All right, let's get right into it. Think about this. For decades, pretty much our entire digital world, I mean everything, has been protected by a very specific kind of lock. And that lock is just really, really hard math problems. But now, a totally new kind of key is being made. And this key, well, it threatens to break every single one of those locks. We're talking about a super high-stakes, invisible race for what's called quantum security.
And it really all kicks off with this strategy that, honestly, sounds like it's ripped straight from a spy thriller: harvest now, decrypt later. It's just a few words, but that one phrase, it describes one of the absolute biggest threats in cybersecurity right now. So, what on earth does it actually mean?
Well, here's the unsettling part. It means that as we speak, adversaries are just scooping up enormous amounts of encrypted data. We're talking health records, financial info, state secrets, you name it, it's being copied. Now here's the catch. They can't actually read it yet, but they're not trying to. They're just stockpiling it, hoarding it all away, and basically just waiting. Waiting for the day when a machine finally exists that's powerful enough to just shatter all of today's encryption. That's the game plan. Harvest our secrets now so they can decrypt them later.
And that brings us right to the heart of the issue. There's this looming event that some people in the know are actually calling the crypto apocalypse. I know, it sounds dramatic, but the reason is simple. That fundamental belief we all have, that our digital locks are basically unbreakable, yeah, that's about to be proven very, very wrong.
You see, the quantum threat isn't just about computers getting faster. That's not it at all. It's about them working in a completely different way. They are literally built to solve the exact type of math problems that our encryption, things like AES that we use every day, is based on. And look, this is not some far-off theoretical thing anymore. Chinese researchers have already claimed that even some quantum systems you can buy today pose a real and substantial threat. And when you see that the whole quantum computing market is on track to hit $50 billion by 2030, well, you know the race to build that ultimate master key is absolutely on.
Okay, so if all the locks we've built using math are about to break, what's next? I mean, where do we even go from there? Well, the answer is kind of beautiful, and it's totally revolutionary. What if we just stop relying on math? What if we start relying on physics instead? The idea is to build a whole new kind of security, one that's based on the fundamental laws of the universe itself.
This brand new defense is called quantum key distribution, or QKD for short. So instead of, these complex math formulas, it actually uses the quantum states of single particles, like little bits of light called photons, to create and share a secure encryption key. And here is the absolute game changer. Its security isn't based on a math problem being really hard to solve. No, it's guaranteed. By the laws of physics, it's a whole different level.
So how does this even work? It's actually kind of genius. Imagine a message that literally self-destructs if anyone but the right person tries to look at it. That's basically QKD. Here's the deal. You send an encryption key encoded on a stream of single photons. Now, there's this fundamental rule in quantum physics. You can't look at something at this tiny scale without changing it. So if an eavesdropper, a hacker, tries to intercept and just measure one of those photons, they can't help but mess it up. They leave a footprint. The sender and receiver see that disturbance immediately. They know someone is listening in, and poof, they just toss that key out and start over. It makes secret interception impossible without getting caught.
And here's the thing. This isn't just a cool idea in a lab somewhere. It is being built right now. And one country has taken a massive commanding lead in putting it to use, building what you could almost call a great quantum wall.
I mean, just look at the timeline of their progress. It's incredible. Back in 2016, China launched Micius. That was the world's first quantum satellite. Just a year later, in 2017, they'd already built a 2,000-kilometer quantum fiber network on the ground. By 2021, they'd connected the two, creating the first-ever integrated space-to-ground quantum network. And then in 2025, they showed off long-distance QKD with a new, smaller satellite. You see the pattern here, right? It's consistent, it's focused, and it is moving incredibly fast.
And the scale of this thing is just staggering. China's integrated network already stretches over 4,600 kilometers. But what's really key here is that this is not some science experiment. It is a working system right now, serving over 150 industrial users. We're talking banks, power grids. This tech is already out in the real world doing real work.
And make no mistake, their ambition is global. In 2025, they used that microsatellite, the Jinan-1, to set up a secure communication link all the way from Beijing to a ground station in South Africa. That's a distance of nearly 13,000 kilometers.
They're not just building a national network, they're building an intercontinental one.
So, the big question is, where does this leave the United States? When you're faced with that kind of rapid progress, the challenge becomes crystal clear. How do you avoid getting left behind in a tech race this critical?
And that sense of urgency, it's absolutely palpable, and it goes right to the highest levels of the U.S. government. This exact issue was front and center at a recent hearing of the House Committee on Science, Space, and Technology.
And during that hearing, Ranking Member Zoe Lofgren, she put it very bluntly. She said, U.S. leadership in quantum technologies stands at an inflection point. We can renew our commitment to leadership through actions, not just words, or be left behind. I mean, the message couldn't be clearer, right? This is a fork-in-the-road moment that demands real action, not just more talk.
And a huge part of this challenge, well, it really just comes down to money, to resources. In 2024, the Chinese government invested more than 4 times what the United States did in quantum R&D. That is a massive gap, and it just shows you the sheer financial power that's driving their ambitions.
But it's not just about the money. The very same congressional hearing pointed out a whole list of other hurdles for the U.S. Things like, just securing stable funding year after year, finding and holding on to a workforce that actually knows this stuff, and dealing with some really serious supply chain problems that have been made even worse by tariffs on the critical equipment you need to build this tech.
So when you step back and look at the big picture, what does all this mean for the future? What we're seeing are 2 very different roads to quantum security starting to form, and they could lead to 2 very, very different digital futures for all of us.
Okay, so on one path, you've got something called post-quantum cryptography, or PQC. The best way to think of this is like software armor. You're basically creating new, much tougher math algorithms that can run on the computers we already have, and they're designed to stand up to the quantum attacks we know about, at least for now. It's a necessary upgrade for sure, but maybe a temporary one. Then you have the other path, quantum key distribution. Think of this as building a completely new highway. It demands brand new hardware from the ground up, but it offers a true long-term solution because its security isn't based on hard math, but on those unbreakable laws of physics.
And when it comes right down to it, this whole race isn't really just about the cool new tech. It's about something much bigger. It's about who is going to control the fundamental infrastructure of secure communication for the future. Who gets to write the rules? Who sets the global standards? And ultimately, who holds the keys to a world where our information can be truly and verifiably kept private?
Which leaves us with one final, and I think really crucial question to think about. As these 2 competing ultra-secure networks get built out, will they even be able to talk to each other? Are we actually heading for a future where the global internet we know splinters into these separate, incompatible, secure bubbles? A world where the word secure might also just mean separate.